Last day we talked about some general ideas about differential equations. We learned what the order of a differential equation is. We learned about different kinds of solutions, particular solutions, parameter families of solutions, singular solutions, and general solutions. What we now want to start talking about is how to solve differential equations. And the next two sections in the book talk about solving first order differential equations. And in section 15.2, we talk about differential equations of first order that are said to be separable. Now I want you to get the idea that we're only going to be solving first order differential equations that can be written in this way. Not all first order differential equations can be written that way. For example, if I gave you the differential equation, this, you cannot write this differential equation in this form. It is impossible for me to solve this because of this cube here. I cannot write it in that form. Cannot be expressed in that form. Right? So we're not solving all first order differential equations, only ones that can be written that way. Right? Now, I think you will agree that if you got a differential equation of this form, you can always say that any function of x and y, namely that f, can always be regarded as a quotient, right? That's not any restriction whatsoever, right? And again, what you're saying is, I want to find functions whose derivative is equal to this over this. And if that's complicated and that's complicated, then this could be a very complicated differential equation. Equivalently, do you agree that you could write this in the form that? Take the n and put it up here, and take the dx and put it up there. So anything that can be written in this form can be thought of in this form and can be written in this form. I don't like this form from the point of view of feeling a differential equation, because it says you've got this stuff multiplying dy, which is supposed to be a little bit of y, and this stuff multiplying a little bit of x. That gives me no feeling whatsoever. But we're going to find, for purposes of this class, it is going to be advantageous to write it that way. Right? A differential equation, meaning this one, is said to be separable if it can be expressed in the following form. dy dx is equal to a function of x divided by a function of y. So this is special, and we're calling it separable. What we're saying is, whatever that function is at the top, it doesn't have any y's in it. Whatever this function is in the bottom, it does not have any x's in it. Equivalently, I could write n of y dy is equal to m of x dx. And now you can see perhaps why they use the word separable. Because if you look on the left-hand side of the equation, all you see are y's. You look on the right-hand side, and all you see are x's. We've separated the y stuff away from the x stuff, and we therefore call it a separable differential equation. Okay? I could also write it, do you agree, in the following fashion. N of y dy dx is equal to m of x. Take the dx back down where it came from, and write it that way. That's the same thing. It's not separated anymore because I do have some dx's on the left. But suppose I now say, let's integrate with respect to x on both sides. We would have the integral of n of y dy dx multiplied by dx is equal to the integral of m of x dx. I simply said, go and integrate both sides with respect to x. Now, the right-hand side is not a problem. If I've got the m function, this says go to integrate. And you are presumably good integrators because you took 1710. Now, what about the left-hand side? What you have to think about on the left-hand side, that this is implicit anti-differentiation. You're saying to yourself, find me a function with y's in it, so that when I differentiate it, I get n of y times dy dx, right? So that's implicit anti-differentiation. Alternatively, do you agree that I could write this? That I could cancel those dx's, and I would have n of y dy is equal to the integral of m of x dx. And now what do you see? Now on the left, you have to take the n function and integrate it with respect to y. On the right, you take the m function and you integrate it with respect to x. All right? Now, be very careful. In going from here to here, what's really taken place is, going from there over to there, you made a change of variable in the integral. You said, I'm going to change from y's, or from x's into y's, right? Because I don't want you ever to say to yourself that you can take an equation and integrate one side with respect to y and the other side with respect to x. That, you just don't do that. For instance, if I gave you the equation of, say, y is equal to 2x, would you do something silly and say, hey, I'm going to differentiate the left-hand side with respect to y, and I'm going to differentiate the right-hand side with respect to x. If you differentiate that with respect to y, you get 1. If you differentiate this side with respect to x, you get 2, and that's definitely not acceptable, right? So if you can't differentiate one side of an equation with respect to one variable, and the other side with respect to another variable, what makes you think you could do it with integration? The answer is, you can't, all right? Could you take this thing and say, let's integrate it? Y squared over 2 is equal to x squared, and let's throw in a constant. Now this is a straight line. What's this? That's a hyperbola. What the heck do you think is going on? All right? So in other words, you do not, in general, do that. All we're saying here is, in the context of separable differential equations, if you've got a differential equation that you separated like this, if you put an integral sign here and you put an integral sign there, you will get solutions of the differential equation, but only in this context, right? And this is the one that I usually like. Yeah? I don't like going through this to this and then canceling and get to there. I will simply start here and say, let's do that. Now, one thing you have to realize is the following. If you do this, you separate it. All right, let's take a nice simple example. So suppose you end up with y dy dx. dy is equal to x dx. All right? So originally, perhaps the differential equation was this. dy dx is equal to x over y. All right? That was the differential equation originally. You separated it and you got this. And then you say, all right, I'm going to integrate like this says. So you write integral y dy is integral x dx. And you do the integration. What do you get? Y squared over 2 is equal to x squared over 2 plus c. You throw on a constant of integration. And you don't have to throw on both sides. one side is sufficient. Because if you put plus d here, then I'll take that d, put it over here, have c minus d, and I'll call that e. So I don't need it on both sides. Now what have you got? What is this? This is hyperbole. Let me put a minus sign in here, just so it's easy. Put a minus sign there, minus sign there, minus sign there. And now what have you got? Now if you multiply by 2, x squared plus y squared is equal to 2c. That's what you're looking at now. You've got yourself a one-parameter family of solutions. Is it general? I don't know, all right? I just don't know. That sometimes is a very difficult thing to decide. Is a parameter family general? And we'll talk about that again later, right? So, but you recognize this, that's a circle. So what are you saying here then? You're trying to find functions such that if you differentiate them, you get minus x over what you started with. And you're saying, these do the trick. But that's not a function. What we're saying here is, if you look at this, that's a function. That's a solution. If you looked at this, that's a function. That's a solution. What we're saying here is when you go through this process of doing this, you're going to get solutions, but the solutions are going to be defined implicitly. Any function defined implicitly after doing this, right, will satisfy the differential equation. So the upper semicircle here is a solution of that differential equation. This lower semicircle is a solution of the differential equation. So again, once you go through the separation and do this, you get solutions defined implicitly. Ultimately, what you would like to do is get them explicitly. And for this example, I could do that. I can solve this for y is equal to plus or minus the square root of 2c minus x squared. Those are explicit solutions of this differential equation. This defines those solutions implicitly. And this is going to happen in every example. Every example, when you separate, you get not explicit solutions, you get implicit ones, and you may be able to solve for the explicit ones, and you might not. So we'll do some examples, and we'll ask the question, once we've got them implicitly, can we get them explicitly? So let's look at some examples of the separation idea. So this was an example to get us going, but I left out some of the terminology that I would like you to say when you solve these separable equations. And I'll introduce it in this first example. And it's what we've seen before. dy dx is equal to y squared. I introduced this differential equation in the last class, and I threw out to you solutions. I just pulled them out of the air and said, I'll show you how to get them shortly. And now I can. This differential equation is separable. I can write 1 over y squared. dy is equal to dx. Bring down the y squared, take up the dx. But you've got to say to yourself at this point, y not equal to 0 because you divided by y squared. All right? Now if you look, right, now this is a function. This is the function y of x is equal to 0. Not a particularly interesting function, but I'm going to ask the question, is that a solution of the original differential equation as given? And the answer is yes. If you differentiate 0, you get 0. And if you square 0, you get 0. So that guy is a solution of the original problem. By doing this, from now on, I'm looking for solutions that are not 0. But y equals 0 is a solution. I'll come back to this point in a minute. So let's carry on. So what I would like you to say here is a one parameter family of solutions is defined implicitly by. I didn't do that in this first example here because I was just trying to point out some ideas, right? But I would like to see that in every problem that you solve by separation. It's defined by, and rewrite it. 1 over y squared dy is equal to integral dx. Right? And we can do this in the context of differential equations. Right? So if we do it, we get minus 1 over y for the antiderivative on the left, and the antiderivative on the right, x and c. So functions that are defined implicitly by this equation are solutions to this differential equation. But I can get them explicitly. I can solve this for y. Take over the minus sign and turn it upside down. Y is equal to minus 1 over x plus c. And that was the solution I kind of pulled out of the air last day for this differential equation. So now we see how I got it. I separated the differential equation, I integrated it to get implicit solution, I solved, and I got me explicit solution. I got me then a 1-parameter family of solutions. But we said this guy is a solution of this differential equation. Is he in my family? Can you get this function by specifying a value for c? And the answer is no. So what do we call this guy then? We say you are a singular solution of this family. So since y of x equal to 0 is a solution of the differential equation, not in the family, it is a singular solution of the family. And you should always be on the lookout for that, right? Sometimes they're obvious, right? This one was kind of obvious. Once I did that, I had to say this, and then I checked on it. It can be very difficult sometimes to find or see singular solutions. Let's look at this example that we've seen before as well. It is an obvious one, but I want to do it by separation of variables to point out something that will happen. dy dx is equal to y. Now, we know the answer to that. Well, let me put a 2 in front of it. We know the answer to that because we actually talked about it previously. Functions that satisfy this differential equation were exponentials. We saw that, right? Because we were good at differentiation functions. Let's show that we can get those functions by separation, and something's going to happen that is worth talking about. I can separate it. dy over y is equal to 2 dx. I have separated. Therefore, a 1-parameter family of solutions is defined implicitly by the integral of dy over y equal to the integral 2 dx. Doing it, integrate this, and you get the logarithm of the absolute value of y. Do this, oh, should have done something here. The fact that it divided by y, I should have put here y not equal to 0. Again, I got that same function as a potential function that might or might not be my family, and he indeed is a solution. Y equal to 0 does satisfy this differential equation. It remains to be seen whether he ends up being in my family or not. Let's carry on. 2x plus c. So So anything defined implicitly by that is a solution to the differential equation. Let's get them explicitly. What you probably would first do is say, let's exponentiate. The absolute value of y is e to the 2x plus c. Let's get rid of the absolute values. Y is equal to plus or minus e to the 2x plus c. Is this the same thing? Plus or minus e to the c, e to the 2x. And whatever you do, and I've seen it happen, is do not write this as e to the 2x plus e to the 2c, or e to the c. That's a disaster, okay? That's not the way exponentials work. Don't ever do that. All right, well, what's this? That is just a great, big, fat constant. Why don't we call it d? d e to the 2x. Now, that is the solution that we saw before. When I talked about this differential equation before, you and I came up with these as solutions, right? Now I've generated them. If we're not particularly bright, I've generated them by separation of variables. Now I gotta ask, is this function, y of x equal to 0? Are you in my family? You are a solution. Are you in my family? And you're going to say to me, yes, I put d equal to 0. But I'm going to say, no, you can't. Because d is equal to plus or minus e to the c, and that cannot be 0. No matter what c is, d is not 0. So this guy, y of x equals 0, is a solution, and he's not in my family. Therefore, at the moment, he's a singular solution of my family. But what if I say, if we allow d to be 0 also, right? And we look at y is equal to d e to the 2x, right? If I allow d to be 0, all right, when d is not 0, I get all the solutions we had before, and if I allow d to be 0, this turns out to be that, and that is a solution, all right? So by allowing d equal to 0, I now capture that solution in my family, and he's no longer singular. So y of x equal to 0 is no longer singular. And I would always ask that. When I get this family, and this guy's a solution, if he's not in, I would always ask, can I do something to get him in the family? And here the answer is yes. Simply allow d to be 0, as well as non-zero. So be aware of that idea. It can happen quite often. So those two examples were relatively straightforward. Let's take one that's a little more difficult. This one. dy dx is equal to 3x squared over 1 minus y. But this time, I'm not going to look for a family. I'm going to look for that solution of this differential equation that also satisfies this initial condition that when x is 0, y must be 3. All right? So I'm not looking for a parameter family. I'm not looking for a general solution. I'm looking for a particular solution of that differential equation that also satisfies that initial condition. But this differential equation is separable. I could write 1 minus y dy is equal to 3x squared dx. It's separated. And therefore, a one-parameter family of solutions is defined implicitly by writing that the integral of 1 minus y dy is equal to the integral of 3x squared dx. And we can do the integration, they're simple enough. Y minus y squared over 2 So I've got me a one-parameter family of solutions. Is it general? I have no idea, but I don't care. I'm not looking for all the solutions. I'm only looking for the solution that satisfies this. So let's see that y at 0 equals to 3. What does that imply? You put a 3 here, and you put a 3 there, is equal to c. So c then is equal to minus 3 halves. Minus 3 halves. So a solution is defined by putting then y minus y squared over 2 is equal to x cubed minus 3 halves. Right? If I want it explicitly, I should now solve this. And I do want it explicitly. I love functions defined explicitly as opposed to implicitly. So consider solving this equation for y. Well, it's really a quadratic in y, agreed? You got y squares, and you got y, and you got other stuff. Normally when you solve quadratics, it's y squares, and numbers. This happens to have some x's in it, but that's not going to bother me. Suppose I multiply by 2, multiply by minus 2. If I multiply by minus 2, I get y squared. If I multiply by minus 2, I get minus 2y. If I multiply this by minus 2 and I take it over, I will get 3 minus 2x cubed is equal to 0. Agreed? So simply multiply by minus 2 and take everything over to the left-hand side. Now that's a quadratic. A is the 1, B is minus 2, and C is all of this stuff. So I want to solve it. I'll pull up my handy-dandy quadratic formula. Y is equal to minus B plus or minus square root of B squared 4 minus 4 A and C. All over 2A. Then, those are functions that satisfy the differential equation and the initial condition. Agreed? But there's 2 of them there. Let's simplify it. Let's do the following. There's a 4 here and a 4 here. Let's pull out those 4s. That becomes a 2. We'll take that 2, and that 2, and we'll cancel. 1 plus or minus the square root of. We took out that 4, that's 1 minus 3 minus 2x cubed, which I'll rewrite as 1 plus or minus the square root of 2x cubed minus 2. How does that look? Happy with that? I hope so. All right. I don't like it, actually. Did anybody spot any errors along the way? All right, let's assume it's correct. I got a bit of a problem. I'm looking for that solution of that differential equation that satisfies that condition, and it looks like I've got 2 of them. Are they both solutions? Well, I would have to check 2 things. I'd have to check, does that function satisfy the differential equation? Does that function satisfy the differential equation? Does that function satisfy the initial condition? Does that function satisfy the initial condition? Let's check the initial condition, right? Something's wrong. Neither one of those are going to satisfy the initial condition, because if I plug in x equal to 0, I got a major problem. Great. So where did I make a mistake? Multiply by minus 2, multiply by minus 2, multiply by minus 2. Here it is here. I'm multiplying by minus 2, and then I'm taking it over to the other side. So if I multiply this by minus 2, it becomes 3. I take it over to the other side, and it becomes minus 3. This one, I multiply by minus 2, and I take it to the other side, I guess it becomes plus 2. So I guess that, all right, so what does that change? That means this is a minus, that's a plus. All right? That means then we pull out, that's a minus, that's a plus. So now the 2x cubed is a minus 2x cubed. And we've got 4 minus 2x cubed. Hopefully that's right now. Now let's check. The initial condition, when we plug in x equal to 0, we will have this. If I chose the positive, I'd have 1 plus the square root of 4, which is 2, which is 3. That looks good. But if I choose the minus, I'd have 1 minus 2 minus 1. That's not working. In other words, the solution is y of x is equal to 1 plus the square root of 4 minus 2x cubed. The other one doesn't satisfy the initial condition. If you check, I believe both of them will satisfy the differential equation, but it was easier to check the initial condition first, and I found one of them didn't work. So this is my solution now. What I would like to say is, because always when I solve a differential equation, I'd like to say, when is it valid? For what values of x is that an explicit solution of the original problem, right? And you've got to say to yourself, it's defined for 4 minus 2x cubed greater than 0. You'd have to have, or you could also have it greater than equal to 0, it would be defined. And that would mean then that 2x cubed is, if we take that over there, is less than or equal to 4. X cubed less than or equal to 2, and therefore x less than or equal to 2 to the 1/3. Is that the answer? Is that the domain of validity for this function as a solution of that differential equation? The answer is not quite. Why not? Answer, if you were to put that function back into this differential equation, and you looked at the left-hand side, it says take the derivative. And if you take the derivative of this, that square root is going into the denominator. And then, if you allowed x to be equal to 2 to the 1/3, you would have a 0 in the denominator. So in other words, all right, solution value for x less than 2 to the 1/3, you cannot allow it to be equal to 2 to the 1/3 because the derivative does not exist at 2 to the 1/3. So there would be our complete solution, corrected along the way, all right, of this problem. Right? That's the function that satisfies this. It prompts me to make the following remark. You should never get a wrong answer for a differential equation, see on a test. Because you can always check, provided time limits, you can check whether this is a solution by putting it back and seeing. Calculate the left-hand side, calculate the right-hand side, and see if they're the same. If they are, you say, good, I got it. If they're not, well, there is the question, is your checking wrong? Let's hope your differentiation is better than your integration, all right? So that when you differentiate here and you plug it here, that you didn't go wrong there, right? So you can always check answers. What I would now like to do is some applications. To me, applications of differential equations, especially for you as engineering students, are most important. For mathematicians, they don't care. They simply say, go find me all the solutions and talk about their properties. For us as engineers, our differential equations are going to rise through applications. And here's the first one. Right? I meant to bring my textbook. Okay? This is going to be exercise 18, modified. Since I didn't bring my textbook, I won't have the numbers correct, okay? But the idea will be the same. Suppose I take some water in a container, and this water is at 80 degrees Celsius. And, because it just came out of the microwave, maybe it's coffee or something like that, right? And I bring it into the room, at room temperature, is a constant 20 degrees Celsius. Let us assume that, all right? Now, obviously, the temperature of the coffee or the water is going to go down. And the question is, could we predict what the temperature of the water would be as a function of T after we bring it into the room? And the answer is not without some additional information. The additional information is that there's a thing called Newton's law of cooling. Newton just didn't invent calculus. He talked about a lot of other things, and particularly he talked about heat flow, right? And you're going to study heat flow in general in Math 3. Here we're talking about a very simple situation, right? And what Newton's law of cooling said in this context says that the rate of change of the temperature of the water is proportional to the difference between the temperature of the water and the room. This is a law, it's called Newton's law of cooling, right, based upon experimental evidence, right? So what we're doing here is we're taking Newton's law and we're going to cast it mathematically. Mathematical modeling is a huge branch of mathematics. It is everywhere. People are trying to model spread of coronavirus. Okay? And all kinds of things are modeled mathematically, right? And this is a bare introduction. If you've got a law to model mathematically, that's relatively simple. There's no law for the spread of the coronavirus, no mathematical law for that, right? So they make up models to try and predict it. So this is your first meager introduction to this idea. Right? So let's let T of T be temperature of the water. And little t may mean then time, right? So what does Newton's law say? It says that the rate of change of the temperature, that's dt. That's the rate of change of the temperature of the water. And he says it's proportional to, so you put in a constant proportionality K, to the difference between the temperature of the coffee and the temperature of the room. So there's our mathematical interpretation of what that law said. K a constant. Could you tell me if and when I find K in this problem, will it be positive or will it be negative? Can you tell me that? And the answer is yes, you can. So that if later on you find it, then it better adhere to what you say now. Well, notice, that is going to be positive, right? The temperature of the coffee is always going to be higher than the temperature of the room. The coffee temperature, water temperature is simply going to drop. What about this? The temperature of the liquid, the water, is going down. It's decreasing. That means the derivative is negative. So this guy is negative. Well, then that tells you this guy has to be negative. Right? So those two guys imply that K has to be negative. So if and when I find k in this problem, it better turn out to be a negative quantity. Some people like to put a minus sign here, in which k would be positive, but I'm not in favor of that. I'll just simply say, hey, let it happen. I'll find out it has to be. I don't like introducing extra minus signs to make things negative. Just let it turn out to be. Right? All right, so what do we got then? Oh, we also have, initially, if we chose time t equal to 0, when we bring the water into the room, it is 80 degrees. So we've got then what we call an initial value problem. Solve this differential equation subject to this initial condition. Right? So we're going to ask, differential equation, how do I solve it? Well, if I look at it, first thing I'm going to ask is it separable, because that's the only technique I've got so far. Later on, we've got other techniques. Maybe it'll turn out to be something else too. But this guy is separable, agreed? You can take and write dt over t minus 20 is equal to k d little t. Take that thing down here, right? And take that thing up there. Now I could write here t not equal to 20. But I'm not going to write that. Reason being, the temperature of the coffee is never going to be 20, right? It's simply going to get cooler and cooler and cooler. But I don't believe that it would ever get to be 20. So I'm not even going to put that there, right? So let's see. Oh, it's separated. So we can say a one parameter family of solutions is defined implicitly by dt over t minus 20 integral k dt. Throw my constant before I forget. Right hand side, easy. kt plus c. Left hand side, you should recognize the logarithm of the absolute value of t minus 20. So says first year calculus. Do I need the absolute values? Not really, agreed? Because t is always going to be bigger than 20, so I really don't need those absolute values. I could replace them with parentheses. You don't have to. I'm going to get the same answer whether I do or don't. So my solution for big T is defined implicitly by this. I want it explicitly. I'm going to exponentiate t minus 20 e to the kt plus c. I'm going to write that as d e to the kt, like I did in a previous example. And now solve. T of t is equal to 20 plus d e to the kt. I stopped for a second and I thought to myself, ooh, this looks like the temperature's going up. But I suddenly remembered, what did we say about k? K is negative. So that guy's a negative, therefore this guy is going to be decreasing as time progresses. And I said, oh, I'm happy again. Right. So let's force on the initial condition. We need AT to be equal to t at 0, and that's 20 plus d e to the 0. So d then is equal to 60. So temperature of my liquid is 20 plus 60 e to the kt. That has got to be the temperature of this liquid in this container as time progresses. Notice as a quick check, if I put in t equal to 0, I get 80. That's good, all right? Remember we said k is negative, all right? So what does that mean? It means as t gets larger and larger and larger, this thing's going to get smaller, 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 this thing's going to get smaller, 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 and therefore it's going to get closer and closer to 20. Exactly what I would expect. Does it ever get to 20? The answer is no. There's no value of t plugged in here, which will turn this into 20. So the temperature of the liquid is going to get closer and closer to 20, but it will never be equal to 20. I don't have k. The reason I don't have K is I don't have enough information. Let us suppose temperature of the liquid drops to, suppose temperature drops to, say, 50 degrees in 20 minutes, perchance, right? I don't know if that's realistic or not, but let's do it, right? So that means that I have some more information that I can put into here, right? It says when you put T equal to 20, so now we're working in minutes, all right? Up until now, the units of little time could have been anything I wanted. It didn't matter. But now I'm forcing units on. So from now on, T is in minutes. So we have 50 equal to 20 plus 60 e to the 20k. Right. Simply substitute it in. Solve it. You take this over here, that's 30. 30 over 60 is a half. So we'd have e to the 20k is equal to a half. If I take logarithms, 20k is equal to the logarithm of half, which is equal to minus the logarithm of 2. And therefore k is equal to minus 1 over 20 log 2. And it is negative. Thank goodness. All right? So we can now say final answer, temperature of the coffee is equal to 20 plus 60 e to the minus 1 over 20, the logarithm of 2 times t. So put the t there. There's the temperature of the coffee thereafter. If we drew a triple graph, it would look like this is T and this is big T. It starts at 80 and it simply comes down towards 20. It's asymptotic to 20. It would look like that. Exactly what we would expect. Right? So there is an application of the separable differential equation for Newton's law of cooling. I want to do one more example, but it's rather large or long, so I think I'm going to leave it until